Okay, our first problem concerns an object that's rotating at 2 radians per second initially. It speeds up to 8 radians per second. Okay, well, I'm going a little fast with that because 8 radians per second would be about like this. Okay, 2 radians per second, maybe about like this. Okay, so it starts out much slower, speeds up, quadruple. It actually goes, I think, from 2 to 10 radians per second, I'm sorry. And it does that while traveling through 30 radians. First thing you want to think about is, what does 30 radians look like? Okay, well, we know that a radian is an angle such that the distance along the arc of a circle is equal to the radius of that circle. Since the circumference of a circle is 2 pi times the radius, it follows that there are 2 pi radians in a complete circle. That is, something that rotates around a complete circle will rotate through 2 pi radians. 2 pi is about 6, so as a ballpark, 2 pi is about 6. So to go 30 radians, well, what is 30 radians going to be? Each 6 radians is going to be 1 time around a circle, so you're going to have to go 5 times around that circle to complete 30 radians. So it's going to start at 2 radians per second, about this fast. It's going to end at 8 radians per second, about this fast. And it's going to go through 30 radians, 5 complete cycles, as it changes its velocity. Also, it picks up velocity or accelerates at a constant rate. So, what do we conclude from the given information? Well, people were pretty quick to say, well, change in the velocity is 8 radians per second. Okay, well, that's a change in velocity. And the 30 radians is like a change in position, but this isn't really a velocity. A velocity means you go from here to there in some time, okay, at least an average velocity from here to there in some time. Here we're just going around a circle and we're not getting anywhere. So we're going to use a different name for this. We're going to call it angular velocity, and we're going to use a different symbol. We're going to use omega instead of v. So omega simply stands for an angular velocity. It's how fast something is rotating. Okay, and instead of a delta s or delta x, it's going to be a delta theta because the angle measures how far we rotate. Okay, so 30 radians is analogous to, a 50 centimeter displacement or something like that, in that it's how far you go in this context. Okay, and 50 centimeters has nothing to do with any of this problem, but just as an example. Okay, now it took a while for people to tell me that from the given information, which was the initial and final angular velocities and the angular displacement, 30 radians, took a while for people to come up and tell me that from the initial information we're given, we could determine the average angular velocity. And that, of course, is 6 radians per second. Now, from 2 radians to 10 radians, for 6 radians per second to 10 radians per second is a change of 8 radians per second. The average of 2 radians per second and 10 radians per second is 6 radians per second. Okay, so we can determine all this from the, this is part of our given information, and this we easily determine from our given information. Not sure why it took people so long to do this, probably because people are using equations rather than thinking. Use equations by all means, but also know how to think it through. Okay, so from this information now, what can we determine? Well, if it goes 30 radians at 6 radians per second, it's pretty obvious it's going to take 5 seconds. Okay, then what can we determine? Now that we know the delta t, well, we can figure out the rate of change of the angular velocity with respect to clock time. And I've got the word average in parentheses here. The average rate of change would be your change in angular velocity, delta omega, that'd be your 8 radians per second, divided by your delta t, 5 seconds. Now, we don't really need average because we said the acceleration is uniform, which means the acceleration doesn't change. In any case, this is the rate of change of the angular velocity with respect to clock time during this whole interval, and it's easy to see that it when we calculate it, we get 1.6 radians per second squared. Now we've got a symbol for angular acceleration. It's alpha. So alpha is 1.6 radians per second squared.